but we need to go in and look at how to compute and interpret the coefficient of determination. So that sounds fancy, but really we've already seen the value, the values that R squared that we saw in our calculator last week. So remember, the R value tells us how strong the linear relationship is. If we know how strong that relationship is, we know how tight the line is going to be, and if there's going to be a really good relationship, if our predictions are going to be along that same line or not. So when we square that R value, so literally take the R value that's from that information and square it, we find what we call the coefficient of determination. So what does that mean other than that it's squared? Well, since we squared it, the R is between -1 and +1. So anytime you square a number, it's going to be positive. So the R squared value is going to be somewhere between 0 and 1. And it could be equal to 0, it could be equal to 1, but it has to be somewhere within that range. And it tells us the explanation. So if R squared is equal to 0, the line has no explanatory value. So one variable does not explain the other variable at all. If R squared is equal to 1, it means the line explains 100% of the variation in response because there's not any variation. Remember, if it's 1, then every line matches up, or every point matches up perfectly with our line. So if you square 1 and get 1, then all of the variations explained. It's a perfect line. So going back to that data that we looked at last time, we had this table of information. This is the scatter plot that we had when we looked at it, and some of our summary information is given here. So we've got the mean for the depth and the time. We've got the standard deviation for the depth and the time. Remember, we can get that from our two variable statistics. And the correlation coefficient that we got there was 0.773. And we had that information, the regression line. This is all stuff from last time. But our regression equation was that time is equal to, and we switched that order around a little bit. We had AX plus B, but remember, now we've changed our regression line just a little bit. So what if we were asked to predict the time to drill an additional 5 feet, but we didn't know the current depth of the drill? What would be our best guess? So 5 more feet from where? And that's just a guess. But what if we were asked to find the amount of time it would take to drill an additional 5 feet if we already know that we're at 160 feet? So to drill 160 feet, we would be at 7.39 minutes. So we can follow that prediction and follow that trend so that we can find that prediction line and that estimation for what's going to come next. So this is our scatter plot that we looked at before. This is the black line is the graph of the line that we had. And that kind of purple looking horizontal line in the middle, that's our mean Y value. So our mean Y value is about 7. So we've got the difference that's unexplained and then the difference that is explained. And the difference that is explained is what that R squared value is representing. So looking at this as an equation, we're talking about variation. So everything together, the unexplained portion and the explained portion has to account for 100% of the variation. That R squared value tells you the portion that is explained by the variation in your variables. So in the data that we have. So that's the explained portion. And then there's this other variation. We don't know why it happens, but it happens. So if we're looking for the R squared value, we literally square the R and we have that prediction. This is how we would write it in a problem. This is the slide I was hoping to get to. So once we determine what it is, we know that the R value is 0.773. If we square that, we get 0.5975. That's 59.75%. So if we change that into a percentage, we always word this the same way. 59.75% of the variability in drilling time is explained by the least squares regression line. So part of this variability, and actually in this case, the majority of the variability, is explained by the trend in the line. We have that other portion that's not explained. We don't know what happens, why there's that variation. But we can explain about, in this case, 60% of that variation. So this is just showing us a comparison of 3 different sets of data. So we've got data set A, B, and C, and we're not going to stop to take the time to type these in today. But it tells us that the variance of y in each one of these data sets, so notice the y values match, but the x values don't, is 17.49. So if we need to find the standard deviation, we need to take the square root of that variance. So looking at these 3 sets of data, so we're not typing them in because we've already got them graphed here for us. Notice in data set A how tightly aligned those points are. That line that goes through those points goes through or touches every point that's in that scatter plot. And notice it tells us that 99.99%, sounds like a commercial, of the variability in y is explained by our regression line. So that variability follows the trend of the line. We know that there's a little bit of variation, especially in those lower left-hand points. There's some variation. The others look like they match up exactly. But that's a really good prediction line. The R value and the R squared value are really strong. If we move on to data set B, it's a little bit more spread out. So we have more variability here. The points don't fall on the line or touch the line as often. So our R value is going to be smaller. So our R squared value is also going to be smaller. So notice 94.7% of our variability is represented here or explained here. And then if we move on to data set C, so all of the Y values were the same, but the X's were the ones that changed. Notice the variation in C. Those points are very spread out. If I were going to try to use that regression line to make a prediction for X equals 10 or 11 or 12, that probably wouldn't be a very good prediction because there's so much variation in that data set. So only 9.4% of the variability is explained by the least squares regression line. These points are all over the place. There's something else going on here that we can't explain. There's something else playing into that variability. So the next thing that we want to look at in chapter 4 is called a contingency table. And contingency tables are just a really good way that we can organize the information that we have. So sometimes the contingency table is called a two-way table because we've got 2 different categories of data that are listed in the same table. So we've got a row variable. In this case, it's a grade that's being represented, A, B, C, D, and F. And then we also have a column variable. And in this case, it's the way you take the class. So this is an interesting example for this point in time. So we've got the traditional delivery, so in the classroom, the online delivery, and then the hybrid delivery. So a combination of the 2. And we're looking at the way the grade distribution is related to these different delivery methods. Each entry inside, so each one of those numbers is referred to as a cell. So this is just like any kind of table that you would make on spreadsheet or Excel or StatCrunch. All of those things would give you a way that you could lay out a contingency table or a two-way table in this way. So when we're talking about the distribution, sometimes we want to add in an additional piece to that contingency table. Marginal distribution, think about the margin of your paper. So the margins around the outside part of your paper. So that's our frequency, our relative frequency for a row or a column. So we would add on an extra column and or an extra row and call it total. It's usually how it's looked at, but it can also be a relative frequency. So it could be like a percentage. But we would be able to find the row totals and the column totals, and those are called marginal distributions. So look what happens when we add that marginal distribution onto the information that we had. All we've done here is add up all of the A's, all of the B's, C's, D's, and F's, and all of the people who took a class in the traditional online and hybrid presentations. And then we have a total for the entire table. So this is out of 743 total students. And we can look, we can make some comparisons. Most of the people took this online or hybrid. There were fewer people who took this class traditionally. And then if you look at the distribution of grades, if we were to plot this and look at how it compares, we've got mostly C's. So most of the grades fall in the middle, and B's come after that, and then F's and D's, and there were the fewest A's for all of the classes. So those are total values. So we can take out one row or column. So I could just look at A's, or I could just look at online, or I can look at the table as a whole, and I can add in these marginal values where I put these total rows and columns on here so we can see that difference. So if I wanted to make this into a relative frequency, the entire table has to be at 1 whole percent. So it has to be 100%. So when we're looking at it as a decimal, it's going to be 1. So finding these row and column totals, we would have to look at it that way. If we want to look at a conditional distribution, so we're looking at a specific condition. So maybe we want to, in this example, it says construct a conditional distribution of course grade by method of delivery and comment on the type. So looking at this condition, we've just looked at the grades. Look at how we can change this conditional distribution into a side-by-side bar chart. So we're looking at a specific condition. In this case, we're looking at the grades in each one. So we can look at lots of different ways that we can compare this. A lot of times when we see information in a table like this, I can make some comparisons. The marginal distribution part helps so that I can see, especially I like it as the totals so that I can see the raw data numbers. Some people prefer it as the relative frequency so they can see the portion or the percentage. So if we moved the decimals on these and found the percents, then you could look at that as a percentage of a whole. But a lot of times, if we have a graph to go along with our chart, if we have a visual way to look at this information, then we've got all of that right there together. So blue is traditional, green is online, the yellowy brown color is hybrid. So we can look at these side by side and make comparisons for grades, comparisons for courses. We could take all of them out except for the blue ones and just look at the traditional grade distribution. Lots of people, when we talked about the bar charts on StatCrunch chapter 2, where you were making the bar charts and comparing the widths of the bins, one of the questions asked for a comparison in which one that you prefer. So I think some people got lost in what the question was asking for that one. Yes, the relative frequency and the frequency tables show you the same thing as long as you label your scale in the same manner. So they should match up, and some people only picked up on that. It's important to notice, and it doesn't apply to this question because we're dealing with letter grades, but in that one we were changing the bin width on a histogram. So it was a histogram that we were looking at, and you had a bin width of 5 or a bin width of 10. That's really what we were asking the question about when we asked which one you preferred, or which one looked better, or which one would be more useful. When you're dealing with a histogram and you change that bin width, it gives you more or less information as far as the way it's split up. Now, sometimes we might want to group it into a bigger set, so we might have wanted that bin width of 10 so that we could see a more consistent graph, or a graph that has less variation in it. If we have a bin width of 5, we have a lot more opportunity for there to be some variation, maybe a little bit of up and down in your bars on your histogram. So just be careful with that and make sure that you're comparing the widths of those bars. Relative frequency and frequency bar charts or histograms, you can make either one. They should give you the same shape. That's part of the point there. So let's change this up a little bit. We have a new contingency table. We're looking at the survival status and demographics of passengers on the Titanic. So we've got men, women, boys, and girls. We've split it up by age and gender. And then we have people who survived and people who didn't survive. So notice at the bottom where we have that relative frequency bar chart. Remember, bar charts are for categorical data. Histograms are for quantitative data. But for this one, we're using a bar chart, but we can still use those total numbers to find the percentages out of that whole of men, women, boys, and girls who survived or didn't. And we can put that information, since this is categorical, into this bar chart, and we can make those comparisons. We can make lots of assumptions here. If you notice, the largest death toll, 80%, was the men, followed by the boys, and then the girls, and then the women. So if you're looking at that darker bar and looking at those death rates, you can look at those percentages. Most of the women survived. Most of the girls survived. So we can make some assumptions as far as how this goes. Here's our, let's see, type. Oh, we've changed our information. We've got insulin dependent type 1 diabetics, and then we've got individuals. So they've got permanent destruction, that's type 1, and then we've got type 2 who can produce insulin, but they're still insulin dependent. So we've got people with different types of diabetes and their survival. And we have our marginal distribution on this one. So just ways that we can organize this information is really important. So there are going to be questions when we talk about contingency tables. There are going to be questions about calculating percentages. Let's see if the question, we just have information here, 902 patients with diabetes over a 5-year period. So here, if we look at this from the table, the proportion of patients with type 1 who died. So with type 1, that means out of those 358 people who have type 1 diabetes, 105 died. So that's 29%, that's 0.29. Looking at the proportion of patients with type 2 diabetes who died, we're looking at just type 2, so just that 544 column, there were 218. So if we find that ratio, if we find that percentage, it's going to be 40% or 0.4. So based on this, we're thinking, well, maybe type 2 is more lethal than type 1. But if we look at this a little more closely, there's something else lurking here. There's some more information that we didn't have. Type 2 diabetes is usually contracted after the age of 40. So there's usually older people who have this type of diabetes. So if we account for the variable of age and divide our patients into two groups, so those that are younger than 40 and those that are older than 40, our data looks much different. Look at type 2. 529 people who were older than 40 and only 15 who were younger than 40. And if we look at that percentage, 218 who died were over the age of 40. So this means that our proportions aren't exactly what we expected them to be. There was more information that we needed. So just because you have that information in a table doesn't mean that you have to go by that 100%. There might be more information that we need in order to make those comparisons. So we could ask some more specific information, and here it reveals that information. We had that lurking variable, which was age, which led us to make that decision. We needed more information before we could come to a conclusion. So this book gives it a name, Simpson's Paradox. It's just the description of a situation where our association doesn't happen the way we expect it to be. There's that lurking variable that we need to look before we analyze what's going on. So that takes care of all of chapter 4.